Here we've got two more limits that I want to look at, and they're actually pretty interesting. So let's take a look at them. First, we've got limit as x approaches -3 of x squared plus 4x plus 3 divided by x plus 3. We've said in the past few videos now that you can evaluate a limit by just taking that x value and plugging it into your function. And if you're not sure where to start, that's always how I recommend, is just take that x value, plug it into your function, and we'll see what happens. So I'm going to take -3 and plug it into my function. So here I've got -3 squared plus 4 times -3 plus 3 divided by -3 plus 3. So let's see, my numerator, I've got 9 minus 12 plus 3. Denominator, -3 plus 3, I have 0. Oh boy, we're going to run into trouble here. I end up in this case with 0 divided by 0, which is not particularly helpful. So I want to try something else this time. I might say, okay, well, if I look at my numerator, that looks like it can be factored. So let's try factoring that first, and let's see if we can evaluate the limit afterwards. We'll see if it changes our answer. So I'm going to try this problem one more time. So here I've got limit as x approaches -3. Let's see, x squared plus 4x plus 3. We can factor that. We want two numbers that multiply to be 3, add to be 4. That would be x plus 3 times x plus 1 all over x plus 3. And then I say, hey, look at this. I've got a common factor of x plus 3 in my numerator, in my denominator. So we can go ahead and cancel that. And then I'm left with limits as x approaches -3 of x plus 1. Let's try plugging it in now. -3 plus 1, I end up with -2. Hey, look at that. There's my limit. So we just had to factor it and simplify it, but the limit did exist. So okay, that's pretty neat. Let's look at this next example, part B. This one is going to be a little bit more challenging, and I think it's pretty tough to solve algebraically. So I've provided the graph here, but I want to, pretend we don't have this graph right here. I'm going to try to evaluate this limit algebraically without using the graph first. So if you're not sure where to start, let's take our x value and let's plug it in. So here I've got 4 squared, so let's see, 4 squared minus 16 divided by absolute value of 4 minus 4. So let's see, here I end up with 16 minus 16 over absolute value of 0. So I end up with 0 divided by 0 once again. I ended up with 0 over 0 last time, too. Well, now I'm going to look at the graph. And the graph, I actually should add 2 little open circles right there. If I look at the graph and where x equals 4 is, here is x equals 4. If I look at the left-hand side of my graph, the left-hand side of my graph being over here, the left-hand limit in this case looks like it's approaching -8. So if I just look from my graph right there, I can look at it and say limit as x approaches 4 from the left-hand side of our function, let's just call it f of x, that's -8. But if I look at the right-hand side of my function, which is over here, and trace my way backwards to x equals 4, we're approaching +8. So that means the limit as x approaches 4 from the right of this particular function is +8. Here in this case, the left-hand limit is -8. The right-hand limit is +8. So this limit really does not exist. And we could have just looked at the graph there, but helpful, I think, to think about the one-sided limits as well. So what gives here? Something kind of odd is going on, because in both of these examples, we ended up with 0 divided by 0 when we initially started. But in part A, that limit did exist. That was -2. But then in part B, when we looked at the graph of the function, we said that limit does not exist. So there's something kind of special about 0 divided by 0. And that's actually this definition that we're going to talk about here. It says, we say that a limit is indeterminate or of indeterminate form if, when we take its limit, we end up with 0 divided by 0. So if we end up with a limit of 0 divided by 0, we say that limit is indeterminate. These limits may or may not exist. If you end up with indeterminate form, you need to go back and try something else. Maybe you need to factor, maybe you need to look at the graph, maybe you need to try something else entirely. So be very careful with these, and I'm going to kind of really highlight these limits may or may not exist. If you end up with 0 divided by 0, don't just say, well, that limit does not exist, because you might be wrong and you're not showing enough work there. It's a really common mistake I see all the time. If you end up with 0 divided by 0, that means you got to go back to the beginning of your problem and you've got to try something different. Now, one thing I want to contrast that with is this theorem right here. It says if we take the limit as x approaches c of f of x divided by g of x, and we end up with L divided by 0, that limit does not exist if L is different from 0. So if we have, say, like 2 divided by 0, that limit does not exist, or -4 divided by 0, or 1.2 divided by 0. It doesn't matter what kind of number we have in our numerator, as long as we have a non-zero number in our numerator, but we do have 0 in the denominator, that limit does not exist. So it's easy to mix these two up, but I want to try to emphasize the difference between these two. If we take a limit and we end up with 0 divided by 0, that is indeterminate form, and that limit might exist. More information is required. In this case, we have to do more work. Must do more work. If we take a limit and we end up with L divided by 0, where that numerator is something other than 0, then in that case, we can just conclude that the limit does not exist. In that case, we don't have to do any more work. No more work is required. So be careful with some of these here. And the next example that we take a look at, we're going to look at some examples which we may end up with indeterminate form, some examples where the limit may not exist, and we're going to just practice seeing if we can kind of tell the difference between these two things.